And welcome, friends. We're going to start our final day of week 2, and it's a beautiful day once again. I think we've had one of the most mild Januaries that I have remembered for quite a while. Um, we got a brand new setup going here. So I've got a dedicated camera, a dedicated microphone. So hopefully the video quality will be a little bit more to your liking, and the sound will work. So I guess if there's more problems that are arising, let me know. Just by way of reminder, for this week, we've got PLC 2 happening tomorrow. Well, I mean, hopefully it's happening during the week, but due by tomorrow. We have homework 1, and we're looking at Tuesday on that. We've got lab number 2 happening tomorrow. Oh, and plus we'll have a quiz on that Tuesday with the homework. Let's see. And that means we're rolling into the week of February 9th, starting on Monday. Alrighty, I think that's about what we've got here. So, we're talking about refraction and lenses and making images with the lenses. So, I was telling you yesterday, let me just grab this because I was telling you yesterday that if I had a block and I cut a converging lens shape out of it, then you'd be left with the diverging lens shape. And so I brought in the block, and I'm just going to make a few cuts on this thing so that we can, all right, like that, and then like this. And so now the block looks like this, and you can see that, well, maybe you can see that if I take and separate the cut right down the middle, like so, I've got 2 halves, and if I separate each of the halves, like this, right? We'll take these out from each other. I'm going to have one that's curved in, one that's kind of curved outwards. And I'm going to take both of these things, do the same with this one. And take these 2 pieces here. If I put these 2 pieces together, I have my converging lens. Now I got to go over here. Right, I'll have my converging lens with what's left over, right? What's left over, part of it goes here, the other part goes there. This is my diverging lens. This is what the diverging lens looks like. Okay, thicker in the tops and the bottom and thinner in the middle. So there's the diverging lens, and this is the one in which we had left off with yesterday. And we were talking about the travel of the rays through it, and then what the ray diagram looks like. So, in fact, we got to do the ray diagram today, I think, right? Converging lens here. What we're going to investigate today is also what happens if I had just this. Would this be a converging lens by itself? Would that work? Instead of having both of them together? What if I just have one of them? And does it matter if I have one this way or one that, like, does it matter if I just flip them around? Is it the same thing, or what's going on? All right, so we're going to try and investigate that a little bit today, as well as talk a little bit about a different mode of thinking. All right, a way in which we can possibly think such that reflection and refraction are more transparent, and we can sit back and reflect on whether it's transparent or not. Also, I apologize for my my allergies. I apparently had a dog sleeping with me most of the night, so that's what happens. We're going to hit diverging lenses, okay? So what we did was we went and looked at the ray diagrams for the converging lens if I have an object outside the focal point, if I have an object inside the focal point. We looked at both of those ray diagrams. We did a couple of calculations. And so today, let's start off taking a look at the diverging lens. We'll look at the ray diagram, look at the quick application of what's going on. We'll characterize the sign convention for the diverging lens. We'll talk about how to make some lenses, how to determine whether lenses are converging or diverging. And then we'll talk about, hopefully, we'll get some time at the end to talk about the principles involved here. So here's our ray diagram. We have the diverging lens, and it's shaped like this. And it has an axis that goes approximately through here. And we've got focal points. Focal point F right there. And the focal point F right there. Excuse me. So I had mentioned last time that what we want to do is come up with a way of drawing the ray diagram such that we don't have to do refraction at each surface, which means that if I were to draw the ray in, I don't want to have to go in here and do a normal here and a normal here. So we were trying to practice that with the converging lens last time, where we use the characteristics of the rays to say, okay, I know I've got a ray coming in parallel with the axis. And we know for the converging lens, it's going to go down and use the focal point and go out through the focal point. So I want to use those same rays that we used for the diverging mirror. I want to use those on the diverging lens, all right? So I got my ruler here. Did I bring my ruler in? I think I did. All righty. So let's go ahead and start drawing these rays. And now you want to make sure that it's not the situation where you're dealing with the same ray diagram as you had with the converging lens. And maybe I kind of remember, maybe I mentioned this last time. If I have my object here and the ray is coming in parallel, okay, we're going into the very middle of the lens, doing all the refraction at the middle. But if I dropped down this way, then that's indicative of a converging lens, and that's not what we have here. And if you're concerned about what the refraction is looking like, which way is the ray going, well then use Snell's law. Go drop a normal in and say, oh, I'm going from air to glass. It bends towards the normal, and then I go glass to air. It bends away from the normal. So if you do that, you should be able to convince yourself that when you look at the outgoing ray from this situation, you should be able to say, well, that's like going along the focal length here, right? It would go like right from along there and leave as if it had come from the focal point. This is ray 1. Ray 2 will pass directly through the middle of the lens undisturbed. So it goes somewhere like there, right? And goes about like that. We do know, I think I talked a little bit about this last time too. Yes, this is a convenient fiction, but we are making the approximation that the displacement of the ray on the far side of the lens is small compared to the, say, the focal length of the lens and the thickness of the lens. Well, not the thickness, the focal length, and the distances of the objects and things like that. Okay, I've already used the focal point over here. Now I got to go use the focal point over here. So ray 3 should aim at the focal point. and draw in here. And then it should come out going parallel with the, why am I dashing that line? It should come out going parallel with the axis like so. Like that. So those are the three rays for a diverging sense. We're going to trace these all back and find that the image is here. And that if we answered the 4 questions about this image, we would find that just as in the last case, with a converging mirror and a converging lens, we had the same images, well, not the same images, but images with the same characteristics were produced. And so now here with the diverging lens, we should be able to look back at what the image produced by the diverging mirror was and say, we should be able to produce an image that has the same image characteristics. So if I answer the 4 questions about this image, I'm going to find that it is virtual. Because the rays out here are diverging, my eye is over here. I'm looking at these diverging rays and I trace them back to find where does it look like they came from. It is upright. It is minified. And it will be on the same side, as well as being slightly closer to the lens as the object. Same side as the object and closer than the object. Incidentally, this is why you see on your rearview mirrors sometimes, what do you see? Objects are closer than they appear. Well, this is not a mirror, this is a lens. But you'd say, well, wait a second, it's already closer. True. But this really has to do with the idea that it's a smaller image. And to our brain, smaller means further away. And we all know approximately what the size of another car is. So when we see it smaller, we assume it's further away. All right, so what we did last time with the converging lens was to ascribe a positive focal length to it. We'll do the same thing in this case. Well, not the same thing. We're going to look at the diverging mirror and ascribe a negative focal length to the diverging lens. Just as we looked at the converging mirror and the converging lens and say, oh, these are doing the same thing for us, give them the same focal lengths, signs, right? Make them both positive focal lengths. We're going to do the same thing here. The mirror and the lens that diverge both give us the same images, or at least they give us images with the same characteristics. So we're going to give them the same focal length sign to deal with. When we use the thin lens equation, at this point then, we could, if I just made up a quick situation here, I think I used an object distance of 30 centimeters last time. So if we said that we had an object 30 centimeters away from a, I'll use careful language here, object 30 centimeters away from a diverging lens. And the diverging lens has focal length 10 centimeters. So, oh, sorry, that got written right through the glare, didn't it? Let's try, where is that? Away from and focal length. There, I just got to remember that that part of the board, I shouldn't be writing it. I'm just going to trace this in here. Oh, right there. Okay, I will try to remember not to write right there. Okay, an object 30 centimeters away from a focal, from a diverging lens of focal length 10 centimeters. If you see a problem like this, what we're going to say is, okay, wait a second. If I just use 10 centimeters, remember then I'm going to be dealing with a converging lens because inherently I have a plus 10 here, right? That's 10. I've told you 10 centimeters, but I have ascribed a negative sign to this focal length for you by saying these words right here, diverging lens. So please be aware that that should trip a flag in your mind. When I say, oh, there's a focal length of such and such, you have to say, well, is it converging or diverging? Okay? From that, you'll be able to say, oh, the focal length is positive or the focal length is negative. Okay? So let's suppose we do this and we say that we've got a 1 over di equal to 1 over f minus 1 over do. And solving for the images now, I would say 30 centimeters for the object distance because that's positive, but the focal length is negative. So you should see this comes out to be inherently a negative number. Minus 1 over 10 minus 1 over 30. So that is basically minus 4 over 30, and therefore the image distance is 7.5, and it's negative. Okay. In addition to which, its magnification, m, which is negative di over do, is equal to positive 1/4 as you put those numbers in. All right. So that tracks with what we've got going here, and hopefully that's a reasonable review of the diverging lens and its characteristics. All right. So at this point, we've drawn all the mirror ray diagrams pertinent to every type of mirror. We've drawn all the ray diagrams for lenses pertinent to every type of lens. Next week, the question is going to be what happens if we have a lens with a mirror? What happens if we have two lenses, or two lenses and a mirror, or a lens and a mirror and another lens, right? Or you're not going to have another lens, but you're going to have a mirror and two lenses like this, right? So keep with the same ideas, what the rays are doing, but I will also say this one other point, which is that remember the whole time we've been doing this, whenever we have an image, we say, well, the image is, if it's a real image, that's not a problem. The light actually is converging there. But if it's a virtual image, we're saying light looks like it's coming from here. The piece I haven't been saying is it looks like the image is here, right? And therefore, if I had an object which was exactly that little tiny size, if I took my object here and I squished it down and put it right there, and then I threw the lens away, I should, in principle, be looking at the same thing. In other words, light would be entering my eye in exactly the same way as when I had the lens there and the object over here. Okay? Light enters my eye in exactly the same way as the object with the lens, or if I squish it down, throw the lens away, and put it right here, exactly the same situation. So when you have an object outside of a lens or a mirror, and then there's a couple of pieces to go through, if I have two lenses to go through, use the image produced by the first lens to be the object for the second lens, and throw that first lens away. You take the image that the lens produces, the first lens, right? You take the image that lens produces, and then you treat it as a completely new image and object situation for the second lens. Okay? And so we'll be exploring a little bit more of that next week when we talk about instruments and putting these things together. Alrighty, so that's basically what we have for the diverging lens. What I want to do here is talk about how do we know. I showed you this lens here, right? If I had this converging lens, okay, I take this lens here and I break it in half, do I still have a converging lens? Or is this now diverging? How do we know? So I want to talk about I want to talk about a way to think about um, analysis of a lens, or if you like to more grandiosely say, well, I'm going to make a lens. Well, how do you do that? Okay, so let's talk a little bit more about that. All right, excuse me. Let's talk a little bit more about that with the following. So it turns out with a little bit more geometry, um, it turns out that with a little bit more geometry, we can take a look at, and some approximations, we can take a look at how do the radii of the two lens surfaces here, right? I've got a radius that's kind of over on this side to make this face, and then I've got a radius over on this side to make this face. How do they combine to make a focal length, right? Especially because we've been talking about the specific case of these sides being curved equally. Well, I was showing you this. Well, what happens if they're not curved equally, right? I've got basically a plane side on one side and then a curved side on the other. What happens to the focal length then? Is there going to be like one focal length that's infinitely far away and one focal length that's only here? How are we going to figure this out? So if I think about the geometry of the situation, and like I said, in a couple of approximations, which I've mentioned a little bit, but I'll say a little bit more thoroughly here, which is that we're considering um, the travel of light rays, which is pretty close down to this axis down here, such that they're not so far away that we're having to deal with a lot of curvature of the lens. We're taking a small arc of the lens here. And and so you might say, well, why? How come we have to look only at these rays? Why can't we look at all of these rays that are coming in hugely? Well, it turns out that when you do that, the surface that you have to create in order to focus all of those rays into a focus, or to create an image, that surface is complicated. It's not a straightforward surface, especially when you're not at infinitely long object distances, like a telescope. Telescopes are easy, right? They're just paraboloids because that's the easiest surface to get something that's really far away and have stuff meet at the same point. But what if you're not infinitely far away? What if you're just right there and you want all of those rays to come here and then focus to a point? That's a complicated surface. So it's really hard to make those. Therefore, if we can make spheres, which are really easy, and we can just say, let's confine all the rays to being close to the axis of the sphere, well, that's an easier situation. And for the most part, that's going to work just fine for all applications. All right. So let's do this. What we're going to do now is take a look at how do we look at the radii of the situation of the two surfaces. We need to think about the sign convention that we're going to come up with, and ultimately, we can also think about the material that we're going to make the lens out of. Is it going to be glass? Is it going to be plastic? Is it going to be something else like water? What if we made a water lens? How would we deal with that? In other words, how does the index of the material play a part in this? Okay, so this is known as the lens maker equation. And what it does is it links all of those quantities and spits you out a focal length. Okay. So I don't know if it's really worthwhile to go through and show you how to derive something like this, but we can kind of sketch it out a little bit and maybe give an outline of how things are going. So we can think about a lens here. We can think about a lens like this. Either way, I've got a radius involved, right? There's going to be a radius of a surface on one side of this and a radius of the other surfaces on the other side. Now, just notice that for this lens here, the radius for the back surface is this one. And the radius for the front surface is this one over here, okay? But that's flipped if I look at the divergent lens. In the divergent case, the radius that makes this is over here. This is not at all in the right place, but I'm just going to draw it here. Otherwise, it's getting a little too busy. This is a radius. Let's call this, this is going to be R2, and this is going to be R1. This is labeled focal. This is going to be R1 here, and this one would be R2 over there. Okay. So we have radii that make the surfaces, and if you've noticed my labeling, I didn't mess that up. They are labeled backwards. In other words, the radius for the far surface in this case is known as R2, but the radius for the surface that is curved the same way here is labeled R1, right? For the near surface, it's R1. So if you think about it as light hitting the first surface, you're calling that first surface number 1, and you're calling this the back surface number 2. So light in our cases has always been coming from the left. That means light hits this side first, light hits this side first. That's why this one's labeled R1, and this one's labeled R1, and that one's R2, and that one's R2, right? So it doesn't have anything to do with the curvature of the situation. It just depends on, okay, I've got light coming in like this. It hits a surface. We got to call this surface number 1, so where's the radius for it? Is it over there or over there? That doesn't really matter so much, but we're going to call that number 1, and then it's going to pass through the lens and then hits surface number 2, and then it's going to leave. Okay. We're going to assume an index of the lens is equal to n, and we're going to assume that the lens is surrounded by air. In which case, that means that the index around the lens is just equal to 1. Okay. So, with that being said, what we find is that if we look at the geometry of the situation, from the case of the thin lens equation, which told us that 1 over f was equal to 1 over dO plus, plus 1 over di. Oh dear. Okay. So we know that the focal length in these situations, because it's a sphere, or because it's a part of a spherical surface, right, the whole thing, but it's just an arc of a sphere. We know then that this is actually equal to 2 divided by r, because it's 1 over f. Remember that f is equal to 1/2 of r, and that radius is the radius that makes the surface. Therefore, this thing is really equal to 2 divided by r. Okay. Now, what if we had different, what if we had different radii going, right? How do we distinguish between an R1 and an R2? So this is just a regular R, so how do we bring in both sides of the lens? Well, we have to think about our sign convention. Now, if you think back to the mirrors, it was fairly straightforward. It was fairly, I don't know if cut and dry is the right word, but it was fairly easy because we could say, okay, if the light is on this side of the mirror, we're going to call that the real side. Everything over there is positive. Everything behind the mirror over here is negative. It's on the virtual side. That gets a little murkier when you deal with the lens. So, just to remind, by way of reminder, the light is leaving the object here, passing through the lens and coming over here, right? The lens is supposed to be transparent. So if the light's over here, we expect it to be making an image over there. Therefore, the real side is this side here. Now, this is only for images, okay? I'm always going to have an object side. So far, we've always used objects to be positive. So I'm going to say my object side over here being positive, but my image side over here is positive. Okay, that means the image side over here is negative, and if you like, the object side over here is negative. That means if I have an object over here, I'm going to have to label it with a negative object distance. I'm just going to put that out there, and we're going to leave that and move on, just to say that and move on. Okay, so the object distance being positive, the image distance being positive is here. So when you look at the sign convention for the radii, we want to say number one is the number, surface number one, radius number one is the one that the light hits first, and then surface number two is the one that the light hits second. Okay, so that's the first thing to know. The second thing to know is that the sign of the radius, right, if it's pointing like this or pointing like this, follows the same convention as the real and virtual side of the lens. In other words, if the radius is over here, we're going to call that positive. And if the radius is over here, we're going to call that negative. Same idea here. If the radius is here, we're calling it negative. If the radius is here, we're calling it positive. Okay? So that's following the same convention as the image distance convention. Okay? Real side being positive, virtual side being negative. Alrighty, so let's take a look. I'll try and make a table of this here so that it maybe makes a little bit of sense. Well, it probably won't make sense, but maybe at least you'll be able to have a way of remembering. Let's see, so surface number one, light has hit that first. And so we're going to have a radius of R1. Okay, and the other surface is the one that light hits second, R2. And I'll just say that light emerges from that surface. So light's incident here on surface one, light's emerging from surface two. Okay, sign convention. The radius is positive if it's on the real side. The radius is negative if it's on the virtual side. In other words, if it bumps out like that, then the radius is over here, and we're calling that positive. If it bumps inwards, then the radius is over here, we're calling that negative. Same idea. right? This is bumping kind of outwards from this side. This is bumping inwards towards that side. So we have, here's our lens. R greater than 0. All right, so I've got the image distance positive and the radius positive on that side of the lens. This is the virtual side of the lens. I'm going to have a negative image distance, negative radius. Okay. So that's just for the images. If it's objects, it's the other way around, right? Objects are positive on this side, objects would be negative on that side. Okay? Okay. So in that case, what I can kind of do here is think about, well, this 2 over r, and by the way, this is going to be very hand wavy. Okay, this 2 over r, how does it come about? Well, if I think about a way to put these radii together, what if they weren't equal, for example? Well, I'd have to say that this 2 over r, if they were equal, it's like I said something like 1 over r1 minus 1 over r2. Okay, because if I did that, R1, take a look at the converging case first. Okay, R1 is the first surface here, right, for this side, and it's got a positive radius. R2 is the second surface over here, but then that's got a negative radius, right, because we've got the radius on the virtual side. So if I subtracted those, I get a positive number because R1's positive and R2's negative. Furthermore, if I made them exactly the same, R1 was equal to R2, then I'd get 1 over R minus minus, in other words, plus 1 over R, so 2 over R, and that's what we get. Okay, now look at it as if it was a diverging case. If it's a diverging case, R1 is negative now because the radius is on the virtual side. So this is a negative number, but R2 is a positive number because that radius is on the real side. Therefore, if I have a diverging lens, this is 1 over negative R1, or if I say they're the same radius, this is negative 1 over R minus 1 over R. In other words, it's negative 2 over R, and that would give you a focal length that's negative. Okay, so this can be used to easily substitute for this. Okay. We do need one other correction in making this, and this is not something that I can really argue easily from the thin lens equation here because it doesn't show up, but I do want to include something about the refraction of the refractive index, right? The refracting power of the surface of the lens of the material, right? How much of a refracting ability does this have? We don't pay any attention to that here, but we are going to need to know it if we want to construct a lens with different radii, because if I have something that really refracts heavily, then I'm going to need to think about what radii I want to use versus something that refracts only very mildly. I'm going to have to change the radii, okay, in order to get focal point be the same, okay? So in that case, what I'm going to write here is that since we assumed what I just erased here, since we assumed that the lens is surrounded by air, what we're going to do is if we use glass, okay, if we use glass has a refractive index of about 1.5. All right, so if I want to change my expression here into something that incorporates how do I find a focal length from that, what I'm going to do is I'm going to have to say that the abbreviated version is that 1 over f is the index of the glass, right? So that would be the 1.5 right there. In other words, this would be left at a net of 0.5 if I subtract air from it. And that way, I'll be able to drop out my 2, all right? So what's really happening here, and like I said, I can't really argue this so well from this perspective, but the idea being here that this is a situation where I get the focal length of the lens from not only the refractive power of the lens material, but also the radii of the two surfaces. Now we're assuming these to be spherical radii, right? And we're assuming that the rays are relatively compact and narrow in a small little region right here near the axis. Now we don't always draw it that way, but that is kind of one of the built-in assumptions. So now with this, we can go and analyze a lens that looks like this. Okay, so now what do we get if I have this lens? What type of focal length do I get? And if I can calculate that, then I'd be able to say, oh, is the focal length positive? Is the focal length negative? Then I would know which way is which. Okay, is it a converging lens or a diverging lens? So let's do that. So let's do that. Let's examine a lens that looks like this. Okay, so what are we going to get if we have a lens that looks like that? Well, in the first case, what we have here is our axis. We would have an object sitting over here. And the question is, if we had focal points, what would they be? All right. So if I'm considering an object here to the left, then light is coming in this way. Let's do light. Light is coming in this way, which means the surface that it hits first is the plane mirror, the plane surface, not mirror. Sorry, it's the flat surface of the lens. Okay, then it hits the glass surface. Okay, so the question is, if I'm going to apply this, I want to start by thinking, what's the radius of the flat side? Excuse me. So let's go with this side. Happy days. All right, let's do this. So this is side number 1. This is side number 2. So what is the radius of each of these sides? Radius R1, what's the radius of a flat surface? Well, that would be infinity. The radius for R2 is going to be some radius. I don't know what the radius of this looks like, but let's suppose it's something like, I don't know, 20 or 30 centimeters. Okay, it's just some number like that. We'll call R2 here equal to, say, 30 centimeters. All right, for whatever reason, or it's just some number. I want to now ascribe the signs to these radii. So R1 doesn't really matter, does it? Because when I look at this, when I'm going to look at applying this, I'm going to have infinity down here. So if it's 1 over infinity or 1 over negative infinity, 0 is the name of that game. All righty. Now R2 is a radius that's over on this side. So that means that R2, I know I'm not drawing them right, I'm just kind of sticking it over here somewhere and just going like this. There's R2. There's R2. It's on the virtual side. So I'm expecting R2 to be negative. I'm going to need to put that minus sign in there. Okay, I noticed that the camera kind of flips in and out of focus. I think it just did it again. So hopefully it's managing. Hopefully you're managing to see that. If I go back to this and I say, all right, let's just assume glass is the material I'm using. So what's the focal length of this lens? If I use 1.5 minus 1, I'm going to use 1 divided by R1, but that's infinity. I'm going to use negative 1 over, in this case, it's going to be negative 30 centimeters for R2. Okay? Sorry. Just going to be one of those days. Okay. All right. Take a look at what happens. What kind of lens do I have here? Well, I'm going to get something in which this is equal to negative 0.5, right? This is 0.5. That's just a half. That's 0 here plus 1 over 30. 1 over 30 centimeters. So this is a half, that's 1 over 30. That means that the focal length is going to be 60 centimeters. Right? Because I got a 2 underneath here that multiplies, and then I got to flip the whole shebang over. All right? Whether or not you care about the 60 centimeters as being the thing that you wanted, notice it is a positive number. That positive should elicit some alarm bells for you, and that should tell you, oh, I know what kind of lens this is. That positive indicates this is a converging lens. And hopefully that kind of appeals to you because, right, if I have the lens like this, okay, there's my lens. Notice that the hallmark of what I wanted to describe this lens like last time was it's thin at the ends and thick in the middle, right? Whereas my diverging lens, thicker at the ends, thinner in the middle, okay? Like that's an hourglass, and this is the reverse hourglass. So if I took just half of this thing, well, it's still thicker in the middle than it is at the ends. Still a converging lens then, okay? Well, what about if instead of going like this, it went like this? Now what happens? Light comes and hits this side first. Now what are we going to do? Well, if we flip this thing around, what's going to happen? Notice that if I flip this around, R2 becomes relabeled as R1, and now is on this side of the lens, which means it's positive because it's on the real side of the lens, and the flat side is on the virtual side. Is on the, well, it doesn't matter what side, it's on the second side. This is now R2, but it's still infinity. So if I flipped it around, I'd still get the same answer because this would now be a positive 1 over 30 minus a 1 over infinity, which is 0, and it would still give me positive 1 over 30. That would give me 60, and it would still be positive. So whether or not I have the lens shaped like this, whether I have it pointing this way or this way, makes no difference. Light still is going to refract exactly in the same way and produce a produce a focal length lens, right? So it'll still produce an image right where right where the lens equation will tell you it would if it's a 60 centimeter lens, okay? And it would be exactly the same if I had two pieces together like this, and it's still, I mean, so now the radius isn't 30 centimeters anymore. Well, sorry, nope, take that back. Now the radius isn't infinity anymore. It's 30 on both sides. Now if I take this, is it still the same, right? Is it still the same as doing this? Well, could I make a lens like this have a focal length of just this one here? Yes, but I have to change the radii. Okay, so let's look and examine what happens if I take this thing and I put one here. What happens to the focal length now? Is it the same focal length or is it different? Okay, now if I have a regular converging lens, if I have this situation, okay, I'm going to take the same 30 centimeter distance and I'm going to say, all right, both sides have a 30 centimeter radius. That means I've got a 30 centimeter that way for R2 and a 30 centimeter that way for R1. If I've got two of the 30 centimeter ones, then what I'm changing this to, right, is 30 centimeters. Okay, if I have R1 being 30 and R2 being 30, notice R1 is on the positive side of the lens, R2 is on the virtual side, so we would ascribe a plus sign to R1, a negative sign to R2, and that means I would do this. I would have two 30 centimeters in the denominators here. One of them's positive, one of them's negative, but I'm subtracting the one that's negative. Okay? And so if I do this, this is going to give me 2 divided by 30, but I'm going to cancel that with the 0.5 out front. That 0.5 is going to cancel the 2. So in fact, if I get this situation, oops, I told myself not to write there. If I get this situation, the focal length is now positive 30 centimeters, exactly a radius of one of these things, all right? Which is kind of fun. All right, so good times. Let's take a look at a half of a diverging lens, right? So if I take my diverging lens and I take just the half of it, I've got a plane side and I've got a curved side. Prediction, probably still a diverging lens if you go by what I said last time. This lens is still thicker at the bottom, thinner in the middle, thicker at the top. So it still has the properties of a diverging lens. Is this what we're going to get when we throw a number or two at it? And let's take a look at this. If I do that, then what I'm going to do is I'm going to say it looks like this, okay, like so. If it's curved on the first side, this would be R1. And this side would be side 2, but as we already noted, R2 is already infinity on the plane side. Told you not to write there. When will I learn? Not soon, apparently. All right, R2 is equal to infinity. All right, let's plug those in and see what this looks like. If I do R1, and I'm going to keep with the 30 centimeter distance here, if I do R1 as a 30 centimeters, notice that R1 as a radius is on the virtual side of the mirror, so I'm going to start off with a negative 30 centimeters here. I'm going to then subtract 1 over R2. R2 is infinity, so this is going to be 0. And lo and behold, you can see I'm going to get the exact same thing as I did in the converging sense. That's going to go to 0. I'm going to get a negative here, though. Now, I'm going to get a 0.5 out front. negative 1 over 30 translates to now a negative 60, and that means we have the diverging. And so as we kind of predicted, still the same basic lens shape, and it gives us the negative focal length, and that gives us the idea that even half of a diverging lens will be a diverging lens. So there are other fun cases to examine here. One in which you might have a lens that looks like this, like a crescent moon. What do you think that's going to do? Well, you can keep thinking the same way about it. Test it out, see what it looks like. Okay. All right, but that is the lens maker equation, and that is how to predict what focal length a lens will have. Okay, so in terms of standard geometrical ray optics, that's pretty much it. So we spent last week on reflection, looking at mirrors and the law of reflection. We've spent this week looking at refraction and the law of refraction, and then lenses as image makers. I want to do, this sounds bad the way I'm going to say it, but I want to do some physics here. And this is all great stuff. Make no mistake about it. The applicability of this particular model of optics is very, very wide. You can apply this to many different things. There are some things you can't. That's fine. But one of the things that we want to do as physicists is push our thinking forward. Okay, so one of my hopes for you in taking this class is, if by chance, and I don't know what the chances are, but if by chance you are not intent on becoming a professional physicist, if by chance that is not where you're going here, what I want to do is have this class enhance your thinking and help you develop it to the point where you have gained some new mental tools. Okay, one of them, as I've stated, is going to be visual thinking, representation of these things with diagrams, and then learning how to flexibly take that representation and put some math behind it. Okay. So that's one of the goals, but one of the other things that we want to do as physicists is try to understand how to think about these two subjects, reflection and refraction. How can we take, and by the way, this is a common thing that physicists are always trying to do, and you probably, if you enjoy reading about science, maybe some history and some new developments and things like that, you'll notice that one of the things physicists are trying to do a lot of is get everything under one umbrella, right? All these diverse, weird phenomena, can we describe them in kind of the same way? So I want to try and give some of that thinking to these two subjects right now. This is a way to think about reflection and refraction such that they both seem to be evident. Okay, so we'll try our best, and we'll see how we go. This is a great way to think about physics, is that how can I think about these things differently, right? How can I think about these things that seem not at all connected? How can I think about them such that they are evident? Right? I want to have a different way of thinking about these things such that they are easier. Now, in describing things like this, it goes generally under the umbrella of something called unification. something that physicists are trying to do a lot of. You may have read a little bit about that and the unifying the forces and et cetera, et cetera. Well, we're going to try and do a little bit of that today and see how it goes. Let's try some unification of reflection and refraction. Excuse me. We'll try to fit them under the same umbrella and see if we can't describe these two apparently distinct phenomena in the same way. All right, so let's go back to the idea I mentioned just a little while ago, or maybe it was at the start of this whole thing, but let's go back to that idea of when we see something, the light entering our eye is exactly the same as the light entering our eye from the image if we had a lens or a mirror there and we were looking at the object in some other place. But the image that was created is exactly the same as having an object of this size right there and no mirror or no lens there. Okay, so let's try and think about that for a minute. So if I have a light, say here, I'm just going to make it a star. Okay, if I have a light here, and let's start with reflection. Okay. I have a light right here, and I have a mirror. Okay. Now the light rays from our star are going to be obviously every direction. Some of them will hit the mirror and bounce off. Okay. Now suppose our eye is up here. Okay. So our eye is right there. The question we might have is, what path does light take if we want to be able to see the star? And you'd say, well, it goes straight from the star into your eye. Okay, let me rephrase my question. What path does the light take if we make it so that it has to hit the mirror first? Okay, it comes from the star, hits the mirror, and then goes into our eye. What's the path that it takes? All right, so, and we know, we have our law, right? Okay, but wait a sec, let's take that back for a sec. Let's just forget that for a minute. The light that we see entering our eye, right, is coming from the mirror like this. If I employed a little bit of the thinking I was just mentioning, which is to say that I threw the mirror away and I just wanted to put the star in a place where light had traveled in a direct straight line from the star into the eye, where would I put the star? Well, I'd have it be behind the mirror, right? This is where you'd see your image. I take the star and I go, okay, well, it's like as if it was down here and the light had just gone like that. Right? That's the straight line path from here to here. Okay, from star directly into eye. That, right? No problem. So what we do is we say, okay, therefore, the path that light takes is the one in which, if we threw the mirror away and put the object where the image is, it's the straight line path from that point to our eye. In other words, it takes light the shortest distance, which is equivalent to taking the shortest amount of time to get from one place to another place. And so you think, well, wait a minute. If light's taking the shortest time to get from one place to another place, is that a little bit more universal than just one time here with a light source and a mirror? Note, however, that if we use geometry properly now, if we use the geometry properly, we'll be able to say that, okay, I know I don't have an object here. The object is really up here. So let's put the mirror back and let's put the object back up here and ask, what path does light take to get from the object to the mirror to the eye? And you'd say, well, we already know this part of the path. the other part must be that one that goes there. Okay, it must be this side here. But if you look at it geometrically, the triangle that you form with this ray right here is exactly identical to the triangle that's formed by this one. All you have to do is just flip it over. Okay, that means this angle equals this angle, and if that angle equals this angle, then this angle equals this angle because this angle and this angle are the same. And that's how you can get the law of reflection. Really quick, right? Easy enough. If these are similar triangles, that angle, and that angle are the same. That is this one and this one. These two angles are the same. 1, 2, right there. But we already know that if you look at it from a parallel situation, that this angle here and this angle here, this angle here and this angle here are already the same. Therefore, if this angle equals that one and this angle equals that one, then this one equals that one, and that's the law of reflection. Remember, we should have measured to the normal, but in this case, it was just easier to do it this way. Okay? So there's your law of reflection. All you have to do is think about what path would light take if I had no object and no lens or mirror, and the object was right there. Well, it would take the shortest distance, which translates to the shortest time path. Okay. Now, when you put the stuff back in there, it still translates to the shortest time path. Is this also applicable to refraction? The answer is yes. So, take a look at this. If we think about, I'll give it kind of a more mechanical example here. So think about this. Suppose that you have a situation, and this is the same thing as we did with the wheels. Right? So suppose you have, this would be great. You have the lifeguard on the beach, and there's a person over here in need of help. Oops, not coming from their arm. All right, help, help. All right, help. So they're swimming around in the ocean in need of some help. There's maybe a shark, and that's going to come get them. All right, but the lifeguard is way over here on the beach. Let me write that somewhere else. I'm not going to do that here. That's the beach. Here's the water. Okay. Question is, what's the shortest distance that the lifeguard would take in order to get from where they are now to this presumably suffering person in the water here? The shortest distance path would be that one, right? This is the shortest distance path, is from here to here. Shortest distance. But look now. How fast can the lifeguard run compared to how fast the lifeguard can swim? I would venture to guess that the running speed is much higher than the swimming speed. Okay? And I would say that this is not a whole lot of running time. It's gonna go pretty quickly, but this is gonna be a much larger amount of time spent with the swimming. Okay? So now I'm gonna ask the question like I did over there, what would be the shortest timed path to get from here to here, based on the idea that the lifeguard can run fast, but swim not as fast. So my contention is that if the lifeguard does something which is very difficult to do, which is not run directly towards someone who needs help, but if the lifeguard spent a little more time running and covered more ground going quickly, and then had less distance to swim at a slower speed, my contention is the lifeguard would get there quicker than just taking the straight line path. So suppose that the lifeguard runs to, say, this point, takes extra time, but goes fast. So in other words, gives up some of the distance in the water during which they would be traveling slower and therefore taking more time, and puts it into running along the beach. In other words, if the person is drowning over there, I'm running this way. It's not a great look, because people are going to be on the beach going, the person's over there, why are you running over this way? You should be going this way. And the lifeguard has to stop. And no, look, I'm explaining to you that I'm actually taking the I'm taking the path of least time and not least distance. And the person's saying, yeah, but the person's already, yeah, no, it's okay. Because I'm going on a shorter time path. And by this time, the person's probably, who knows what's going on. But anyways, point being here, that if you spend a little extra time running where it's quicker, you're giving up the distance in the water, which is good because that's taking more time anyway. So my contention is, in fact, that the time is shorter along this path, not along the straight line path. And lo and behold, isn't that what a refracted path looks like? A refracted ray of light would indeed, if it's going higher speed to lower speed, right? Or if you like, lower index to higher index, that bending is exactly what would happen in the situation of light going from faster to slower speeds. Okay? So really, the thinking of this is that light takes the path of least time. And this is a very famous idea due to Fermat. Back in the late 1600s or early 1700s. I don't quite remember. But nonetheless, it's a principle. So I want to take a minute here to organize the structure of knowledge that we're building, which is, and by the way, this is how it always should be, I think, in physics, is that we have rules, right? We have rules. There are rules about things like springs. So if I stretch a spring and it bounces back, there's a rule about how much force there is, right? Called Hooke's rule. Or there's Coulomb's rule about how much force charges feel between one another. Okay, fine. But then there are laws, and the laws describe the rules, right? The rules are not universal, but the laws describe more. But then, right, so we had the law of reflection and the law of refraction. But now above that, we have the principle. This is a principle. So in a way of our thinking, this is a principle. This is the canvas this is the tent under which the laws reside. Okay, this is how we think about things in order that the laws make sense to us in an intuitive way. And you just think, oh, well, if light wants to take the if light wants to take the path of least time, then it's going to do this. Okay. So whether it's reflection or refraction, the principle is that this is what happens. The principle of least time. Now, it turns out that this is highly more applicable than just to light. And it also spawns a number of really interesting offshoot questions. One of which is, well, how does light know to take the path of least time? How does it know to do that? Now, this opens up a whole nother can of worms, which we're not quite prepared to deal with right now, as well as apparently giving light sentience, which certainly it doesn't have. But nonetheless, you might ask, say, can we describe why it does this? Why does it take the path of least time? What's the reasoning behind that? And maybe we can talk about that. That might be a future That might be a future class by itself right there. All right, but I hope that you have enjoyed this elevation of your thinking to a higher plane of existence. We are into principle land here. So this is how we think about all of those laws that reside underneath. And it's a mode by which you can sometimes see answers to problems much more quickly than if you just go grappling around trying to apply laws to things. All right, so I think that will probably wrap it up for today. Uh, we have the lab tomorrow, which is going to be on refraction and lenses. So hopefully you have a lab kit. That lab will be due on Tuesday. I will be grading lab one probably soon, a couple of times, but it should be done before lab two is due. So that should be there so I can give you the feedback on lab one. PLC 2 is for Friday. Homework 1 looks like it's Tuesday also, and quiz day on Canvas. So, with that being said, I will see you for Lab 2 tomorrow or whenever you choose to see that. And in the meantime, have a great rest of your weekend, and we will reconvene on Tuesday of next week. Happy rest of your time, and enjoy some hopefully good weekend time. And it's not least time. Light for light, it's always the least time. But for us, hopefully, it's a good, solid weekend. All right. Good luck. We'll see you later.